Okay, so good morning and welcome to this morning's session. My name's James Cole. I'm a researcher at King's College London, and our symposium today is looking at modelling population variability and heterogeneity using neuroimaging. And I'm lucky enough to be joined by three great speakers from different universities. So hopefully we should have four interesting and complementary talks for you this morning to talk about how to progress from the mean using advanced analysis, brain diseases, and neurodegeneration. So I'm going to get started talking about the central tendency dependency. So the classic case control design is very, very commonly used in neuroimaging. And in this design, we have a group of patients and a group of controls. And we simply compare the groups to see if there is an average mean difference. However, this design presupposes one very key assumption, and that is that the groups are homogeneous. But actually, clinical experience suggests that really that homogeneity is unlikely to be valid, both at a clinical level, but also at a neurobiological level. And there are lots of different configurations of what actually the reality could be underlying the differences between patients and controls. I should give credit to Andre Marquand for letting me use this nice slide of his as well, actually. This isn't my picture. So it could be that the controls are homogeneous and there are different subgroups of patient groups. It could be that the patients represent one end of a continuum, which is just normal variation within the sort of general population. Or it could be that maybe the controls are homogeneous, or maybe but the patients are actually a mixed bag of some people who fully express a phenotype and other people who only partially express that same phenotype. And that's particularly could be the case if we're looking at neurodegenerative diseases, where we're particularly interested in pre-syndromal phase. And if these three configurations are true, the classic case control design, which depends on measures of central tendency, is not necessarily going to capture individual variation that could be clinically useful. To give you a more concrete example, these are some data from the ADNI study. These are measurements of AV45 PET uptake, so a measure of amyloid binding. And these are bar charts that show you the difference in amyloid between healthy controls, people with mild cognitive impairment, and people with Alzheimer's disease. And you can see that there is a significant difference between the three groups. However, if you take one thing away from this talk, is that I strongly recommend not to use bar charts for interval data, because I think they can be quite misleading. Because if you actually look at the box plots, you can see that there's a really big spread in the groups. And that tells you a bit more about how the data is distributed, and maybe changes your understanding of what these measures actually mean. If you go a stage further and you actually plot all the individual data points, you can really see that there's actually a very wide spread across the groups. And now the kind of increased amyloid in Alzheimer's looks a bit less compelling than previously. If we plot the means for each group, you can still see there is that increasing linear relationship. However, 14% of the controls have higher amyloid levels than the mean in the Alzheimer's group, and 17% of the people with Alzheimer's have less amyloid than, on average, the controls do. So how do we understand these controls with high amyloid and these AD patients with very low amyloid? What does this mean? And for me, this calls into question this understanding that amyloid is a kind of characteristic. Amyloid increase is a characteristic of Alzheimer's disease. And the reason that this is important is that making inferences based on mean comparisons has consequences, and inferences inform understanding. Now, most scientists probably would acknowledge that if we report a mean difference, we're aware that it's a slightly more complicated and a slightly messier situation than just the means that we see. However, we're incentivized to really talk up mean differences and maybe give them undue importance in order to make our publications seem less complicated and have greater clarity. But also these inferences go beyond the scientific realm. They influence clinicians. They certainly influence the media. They influence the public, and they influence the policymakers. So decisions get made on the basis of some of these inferences, and a lot of the complexity is lost. And they also influence drug companies. And just as an example of how important some of these influences can be, last year, Eli Lilly cancelled their phase 3 trial of solanezumab, which is an amyloid clearing drug. And apparently, they spent approximately $1.5 billion trialing this drug, and it failed at phase 3 trial. And that was all based on this inference that because there's a mean difference in levels of amyloid in Alzheimer's, then this is the way to treat it. But the drug didn't work. So these inferences can be very influential. And for me, there's an important kind of consideration of comparing kind of inference versus prediction. And I give credit to Danilo Buzdock for his nice paper that really looks at this in much more detail empirically. But in brief, inference is basically, does X have an effect on Y? And we normally operationalize that by saying, do groups differ on average? And here, the relationship between the sample size and your statistical significance is really important. Whereas prediction is more, can we take some measures of, can we predict values of Y by taking measures of X? And in this way, we're trying to learn patterns in the data, sort of relationships between X and Y. And the advantage of this prediction is it's much more amenable to individualized prediction. So we can take these models and we can just apply them to one new individual rather than just reporting on group average effects. So why is this particularly important at the moment? Well, there have been very few disease-modifying drugs approved for brain diseases. And as we're all probably aware, brain diseases, as population is aging globally, brain diseases are becoming more and more important. Group average measures, using measures of central tendency is kind of ill-suited to making individualized predictions, and that's not going to help us with efforts to move towards personalized medicine. We're all getting bigger studies at the moment, and that means we're getting lower p-values, but actually more and more things are becoming significant on average, but the effect sizes are the same. And this is important because we're going to potentially get lots more significant results on group averages, but it doesn't necessarily mean these are going to be promising leads for tailoring treatments to patients. But bigger studies also provide an opportunity to try different analysis methods that we couldn't use previously. Very broadly speaking, you can group these different analysis methods that we're going to talk about today anyway. One approach is to model the population across the distribution across the population. And the simplest way of doing that is just to consider this as a Z-score. There are other ways of looking at this. You could, for example, look at modeling within group heterogeneity to try and understand what the kind of the lay of the land is within a group, and clustering methods are very useful for that kind of thing. So for the next 7 minutes, I'm going to talk about my approach to looking at this idea of modeling individual variability and in the context of the population. I'm going to talk about a biomarker I've used called brain predicted age. So the idea is that you derive a statistical model of brain aging. This can be quite powerful. The brain changes as we get older, so there's actually quite a lot of variance to play with in terms of building statistical models. But also brain aging has negative consequences. As people get older, their cognitive performance declines and their risk of neurodegenerative disease increases. But also importantly, brain aging will obviously co-occur with all chronic diseases, whether they're brain diseases or not. So as time passes, your brain is changing. And if you've got a disease, there's going to be some interaction with that. So my research is using MRI-derived measures of brain structure as an aging biomarker. And the idea is basically, hopefully you can see that, is to model healthy brain aging in a large sample of healthy individuals, which you can see in this grey line. And the idea is to then look at different individuals, different points on this kind of spectrum, and see how much they differ from the healthy group, and then measure that difference and use that difference as a biomarker of kind of age-adjusted brain health. The idea being that the nearer you are the symptomatic threshold, the worse your brain health is for your age. So I won't go into too much detail, but essentially we did this by getting about 2,000 images from publicly available data sets of healthy individuals, and then training a machine learning model to predict chronological age, which it can do very accurately with explaining about 89% of the variance. In this case, we used Gaussian processes regression, but there's actually lots of other ways of doing it. And then once you've got your successfully trained model that you've cross-validated, you can then take one single individual and you can apply this, the model coefficients to that individual, and you can get a prediction of how old their brain appears. And then you can compare that prediction with their real age, and that can give you their brain predicted age difference, whereby a positive number indicates their brain appears older than you would expect, and a negative number suggests their brain appears younger. We've applied this in various different contexts, and we've shown cross-sectionally that diseases can result in increases in brain predicted age in the context of traumatic brain injury, older adults, well-treated adults with HIV, people with epilepsy and with Down syndrome. But what's particularly interesting for me is that we've looked at this in the context of predicting future health, so not just cross-sectionally, but using longitudinal clinical data. So this is work done by my PhD student at Imperial College, Sebastian, who's got a poster on this, and he did a talk earlier in the week, where we've taken brain predicted age and we've combined this in the ADNI dataset with a range of other biomarkers, and we've looked at predicting conversion from MCI to AD over the course of 3 years. And we've seen that, that taking this global, more general measure of brain health actually adds unique variance to the prediction of conversion alongside things like hippocampal volume, CSF measures of amyloid, and PET measures of amyloid. And importantly, the model that we've used takes into account three-way interactions between these different variables, and that's led to a significant increase in the sensitivity of the approach to detecting people who progress. A lot of the papers published in this area tend to focus on the balanced accuracy, but in the context of MCI conversion, you really want to be sensitive to those who are going to progress, rather than just specifically picking up those who are stable. Another context is work done with the University of Edinburgh using the Lothian birth cohort from 1936, which is a study of adults born in 1936. We had MRI data approximately age 73, in nearly 700 individuals. And what we were able to show in these individuals is that they're, so this is a really great study. Partly, one of the strengths is it's linked to the health records in Scotland, and their mortality is ascertained very regularly throughout the study. So about 10% of the sample had died up to the age of 80 since they were scanned. And we were able to show that those who had died had an older appearing brain at baseline. And actually, we could use their brain predicted age as a regressor in a Cox proportional hazards model to predict how long it was till they had left to live. So it does seem to be a kind of general brain predicted age in this context, seem to be a general predictor of longevity. We've also done some work with University of Graz in Austria, looking at the Austrian stroke prevention study. This is a longitudinal study of community-dwelling middle-aged and older adults. And we were able to show that we could track their brain aging over time quite nicely. So as time passed, the brain predicted age sort of moved on at the expected rate. But what was particularly interesting is that we were able to show that their baseline brain predicted age predicted the amount of white matter hyperintensities that accumulated over the course of the study. And white matter hyperintensity is potentially a marker of cerebrovascular disease, and which is a risk factor for stroke, and that's something we're going to look at in future. And the final bit of data I'm going to talk about is in multiple sclerosis, and this is a big collaboration with people from Imperial College London, University College London, and the Magnim's consortium. And we had access to a lot of data, about 3,000 scans in total, over 1,400 MS patients of different subtypes, and lots of longitudinal neuroimaging and clinical data. And in some cases, follow up to 15 years. And what we're able to show is that in red, you can see the relapsing remitting MS patients. There's a big increase in brain predicted age on average in this group, but there's also a very wide spread. And that spread significantly correlated with their expanded disability status scale, which is the EDSS is a common measure of disability in MS. And the more, the higher their brain predicted age at baseline, the worse their EDSS score got over time. And we could even use that, and we could even predict, we could operationalize that in a survival analysis where we use their brain predicted age as a regressor to predict their rate of progression in future. And you can see in the image that those with older appearing brains at baseline were significantly more likely to progress to worse levels of disability across the study. So those are some applications of brain predicted age. So I'll just sum up now. But my observation is that there's a common dependency on measures of central tendency in neuroimaging applications of brain diseases, but also in other areas of biomedicine, to compare groups and then make inferences based on those group comparisons. But the problem is that those inferences are rarely helpful in clinical practice, and it's because they're not individualized. And obviously, when someone turns up in a clinic, you want to know what to do in that individual circumstance. Brain predicted age is one way of coming up with an individualized marker that places someone in the context of what their brain structure should look like for their age, is an alternative measure, but there are others, and we're going to hear about some of these other approaches today. And it's my hope that actually by progressing away from just using the mean to understand how the brain changes, we should be able to enable more clinically relevant measures that should help us come up with treatments for brain diseases in future. So with that, I'd like to thank you for your attention and invite any questions.
Clarification question. Also, thanks for the great talk. How are you said you were using the brain age prediction and then verifying whether the brain appears younger or older, but how are you verifying the classification accuracy or the accuracy of your model if you don't know someone's brain age, actual brain age? How are you?
So we verified the accuracy of the model in the training data set. So we use tenfold cross-validation in this case. Okay. And I could have talked about it today, but the mean absolute error of that model, which has about 2,000 people aged between 18 and 90, the mean absolute error is about 4.5 years. So yeah, there's still a bit of room for improvement, and a few other people have come up with slightly better methods. But generally, yeah, so the point is we validate it in the training set, and then you assume that the prediction in the test set is in the right ballpark. So.
Thank you.
Thank you for that great talk. I'm curious, you had mentioned on one of your slides about the potential for traumatic brain injury. And I'm curious if you've looked at this as a precursor to a kind of accelerated brain aging in later life. And I'm also curious about the time scale if you are going at the other end of the spectrum in development, where changes in brain development over a course of a year could be dramatically different, even though there's the same calendar age. They may be within the same calendar year. I don't know if that gets that time scale gets factored in.
Yeah, so to answer your first question, we have looked at it in traumatic brain injury in terms of taking the relationship between time since injury and their brain predicted age. And it appears that the longer since injury, the greater the brain predicted age. And we inferred that this is an accelerated effect. So it does suggest that it is increasing their risk of neurodegenerative disease. We haven't looked at it longitudinally in a proper study yet. The second question about development, this is something we could probably talk about a lot. I have deliberately avoided looking at the developmental end of the lifespan because I think intuitively brain predicted increased aging in older life is intuitively a bad thing, but increased aging in younger life is hard to say whether, if a 10-year-old has the brain of a 14-year-old, is that a good thing or a bad thing? And I don't know, but you can use these methods to predict age in adolescence, and people have done that, but I'm not so sure about its use as a biomarker intuitively.
Thank you.
Did you have one last question?
Yes, thank you for your talk. I just don't understand. So you are saying it's important not to just compare means, but aren't you also just comparing mean of brain age gap between groups?
In our results there, we were looking at using it as a baseline marker to predict outcomes often use things like Cox proportional hazard models or other kind of statistical approaches to predict changes in the future rather than just looking at mean difference. So for me, it's not just the group differences, but it's the variability and how that's relevant that is the most interesting thing, I think. Okay, we should probably move on. So thank you very much. And